Hello, welcome to Saurav Sir's classes. It is Analysis of Variance Part 2 video. From the previous video, we have found at the end TSS is equals to SSB plus SSE. Now, let us suppose this table of observations where 1, 2 and k are the factor levels. These are the ith observation, jth observation of ith level. Now, the factor total can be given as T1, T2 and so on till Tk. Note, here we are assuming that different samples may or may not have same size. So, the sample size of each sample is represented as Ni. Now, this Ti is the sum of y11, y12 and so on till y1Ni and similarly till Tk. And G is the grand total, that is summation of all the values Yij. Now, we can determine TSS, which is equals to summation I is equals to 1 to k, summation j is equals to 1 to ni, yij minus y double naught bar the whole square is equals to summation I is equals to 1 to k, summation j is equals to 1 to ni, yij square minus g square by n, where n is summation of ni's. I is equals to 1 to k. And G, as I have said, is the grand total of all the observations. SSB is equals to summation I is equals to 1 to k ni into yi naught bar minus y double naught bar ka square, which is equals to summation I is equals to 1 to k Ti square divided by ni minus g square by n, where Ti is represented as the sum of observation under ith factor. And by the previous formula, we can find SSE as TSS minus SSB. This TSS, SSE and SSB follows chi-square distribution with n minus 1, nk minus 1 and n minus k degrees of freedom. This is for TSS, this is for SSB and this is for SSE. Dividing the sum of squares by their respective degrees of freedom, we get Mst, which is equals to TSS divided by n minus 1, Msb, which is equals to SSB divided by k minus 1, and Mse or mean square error, which is equals to SSE by n minus k. This Mse is unbiased estimate of variance sigma square, and MSB is the variance due to different factor level. Now, if our H0 is true, then the means of our different samples with respect to different levels of factor, though different, but the variability will not be high, or MSB will be small. But if the variation among the means of respective samples is large, then this MSB is expected to be large. On the other hand, if the variation among the components of same sample is large, then MSE will be large. Hence, this ratio F is equals to MSB divided by MSE is appropriate test statistics for testing the null hypothesis H0 is equals to mu1 is equals to mu2 and so on till mu k. F statistics for this test is given as F is equals to MSB divided by MSE, which is equals to F k minus 1 comma n minus k, where k minus 1 and n minus k are degrees of freedom. Let F0 be the observed value of F statistic. Then we reject the null hypothesis H0 if F0 is greater than F alpha k minus 1 n minus k, where alpha is the level of significance. If F0 is less than F alpha k minus 1 n minus k, then the null hypothesis cannot be rejected, and we will conclude that the means of all the groups are almost similar. In other words, different levels of factor do not cause a significant effect. Anova table for one-way classified data. The table is constructed in the following ways. Source of variation, between the factors, and within factor levels or error. The next column would be for degrees of freedom. For the between factor levels, it would be k minus 1, and for error, it would be n minus k, giving the total of n minus 1. Then sum of squares, which would be SSB, SSE and TSS. Then mean square, it would be MSB, here MSE, and then FO, which would be MSB divided by MSE. So this is the Anova table for one-way classified data.